In this tutorial, I will try to walk you through the Mesa, I don't know what the correct pronunciation is, which is a Python library, okay, that can be used to do agent-based modeling, okay? So I'm gonna show you the documentation, okay? So it's a pretty mature project, as I understand. It started a few years ago, actually 2015 I see here, so 10 years ago, not a few years ago. And I guess the developers and they can contact me and tell me if I'm wrong. I think they wanted to build a Python library for agent-based modeling because the most popular library is NetLogo. So I think NetLogo was made by Northwestern University in Chicago. And it's the most popular agent-based modeling. Yes, okay, the developer is Northwestern University, okay. It's in a beautiful place in Evanston, Illinois, if you guys have never traveled there. Anyway, today we'll walk through this library, Mesa, which is a Python library, okay, and we will use Google Colab, and I have the Pro version, which costs I think 11 euros per month. It should be $11 per month in America or something like that. And anyway, I have a very limited experience with agent-based modeling myself, so you will see me wrestling through the project and struggling to make it work and so on. All right. For the record, I used agent-based modeling and complexity theory as it's known. As it's known in a project I worked with back in the day. It was in archaeology. We tried to simulate how people moved in the ancient Roman Empire. And it was my first exposure to computational social science, let's say, okay? Again, my background is in physics, but nevertheless, I find some things fun and I try them anyway. So let's start by installing Mesa, because if we try to do import Mesa or Mesa, I don't know. I'm pretty sure it's gonna complain. It's gonna take some time until until the notebook loads. Anyway, so it doesn't exist, so you have to install it in Google Colab. You have to use the exclamation point and then pip install, and you see how the AI already detected what we want to do, which is crazy. We're living in crazy times. So this is gonna install the latest version, okay? So, by the way, as a teacher or a professor or whatever, I am not the type that really likes to feel exposed, let's say. I mean, if I teach, I want to be 100% sure about what I'm doing. In this tutorial, if we exempt the part that is the programming part, as far as agent-based modeling goes, I don't feel not even 50% competent, maybe 30% or something like that. But anyway, it's good to try new things, so let's go. Okay, so what is agent-based modeling, first of all? So we are gonna go here and read from the documentation. So getting started. So Mesa is a modular framework for building, analyzing, and visualizing agent-based models. And agent-based models are computer simulations involving multiple entities, which we call agents, acting and interacting with one another based on their programmed behavior. Agents can be used to represent living cells, animals, humans, even entire organizations or abstract entities. Sometimes we may have an understanding of how the individual components of a system behave and want to see what system-level behaviors and effects emerge from their interaction. Other times we may have a good idea of how the system overall behaves and want to figure out what individual behaviors explain it. Or we may want to see how to get agents to cooperate or compete most effectively. Or we may just want to build a cool toy with colorful little dots moving around. This is not what we want to do. What we want to do is to simulate an economy. Okay, everybody talks about the economy. We have that quote by Bill Clinton. Let me find it. Let me jump back to the Brave browser for a moment because I like it more. No commercials. By the way, for those of you who are wondering, this is a paper on the Poschel teller, sorry, potential, which I was studying when I wanted to make a tutorial that I also uploaded on YouTube for how to use neural networks in quantum mechanics. But anyway, I digress. So, Bill Clinton economy quote. So, it's the economy, stupid. Yeah, I remember it now. So, I'm not going to open any videos because I'm afraid about copyright stuff, copyright laws and such. So, where were we? Yes, we installed Mesa. Okay, what do we do next? By the way, you don't need any GPUs or anything. For those of you who are familiar with Collab, you can do change runtime type, and then you can change the environment. You can actually do Julia and R in Google Colab. I never tried it, but it's possible, I guess. And then as far as accelerator goes, you can just use a CPU, which is what we do, and it's really cheap. And in the free version, this is what they give you, I think. And you can also use GPUs, but that's for neural networks or more advanced stuff. We don't need this, okay? And runtime version, I don't know what that is. So anyway, so cancel because we don't want to do anything. So as I was saying, we will be modeling an economy. So an economy consists of a central bank, okay, which is the Federal Reserve, say, in America, or the European Central Bank in the European Union. I'm not sure about other countries. It doesn't matter. The central bank, the idea is that it creates money, right, out of thin air, pretty much. Okay, this is my understanding. Okay, I took how many classes? It's been so long. I took a class in economic theory back in college and another one in economic history and international economy, but that's like 20 years ago. So I have a very vague understanding of how economics work. But you have a central bank that creates money, lends the money to commercial banks, like local banks. Okay, every country has local banks that kind of like get loans from the central bank, and then they give loans to people. People have to return money to the local bank if they take out the loan. We're not going to implement complicated stuff. We're going to make it super simple. So the next step, I guess, let me see. We will import everything we will need. So in agent-based modeling, as we said, we create agents that interact with each other pretty much, and that's what we call an agent-based model. So for example, an agent-based model could be, what's a good example? The one we're about to do. Like we will have persons, like people, interacting with local banks, not with each other. Okay, this is a simple model. And then local banks interacting with the central bank. Okay, and we will run this simulation for some steps, as they are called, which and these steps are time units. Okay, and see what happens. So let's import some libraries we will need. So we will need random. If you hover over this, Collab shows you what the module does. So random is a random variable generator, uniform bytes between 0 and 255, integer sequences, distributions, blah, blah, blah. Okay, so we need random numbers, we need NumPy, and already the AI is trying to help us. I think you can disable it, but I don't want to do it. I will leave it as it is. We will actually need matplotlib, so that's a good import. Matplotlib dot pie plot. Okay. We will need seaborn, and we will need this actually. So from Mesa, we will need the class agent and the class model, and we will also need the data collector. Let's go see what these do. So model is the base class for models in the Mesa ABM library. This class serves as a foundational structure for creating agent-based models. It includes the basic attributes and methods necessary for initializing and running a model. Okay. Attributes are running and Boolean indicating if the model should continue running, steps, random, and something called RNG. I don't know what that is. And okay. And then if we go to agents, this is the base class for a model agent in Mesa, and so on. Okay. And it also comes with a position attribute, which we will not use actually because we don't need position in this simulation. All right. So again, NumPy is for numerical operations. Matplotlib and Seaborn are for visualizations. And then we also import the Mesa components we need. So this is an agent-based model. Actually, let's run it. Okay, let's see. No issues. Perfect. Okay. To create agents, let's go to the library over here. Okay, to the documentation. I'm sorry. And okay, this is the overview of the library, and they tell you what you need to implement. So, for example, you need a class called myAgent. A class that is going to represent your agents. So in our case, we will need 3 such classes, one for the central bank, one for the local bank, and one for a person. And you see how each agent class takes an agent class from the library itself, from Mesa, okay? And then you have to initialize it like that as they show us, and so on. Let's go see, okay? And we need to call this super.init to inherit from the agent class of Mesa, okay? So let's type in the central bank. So let's call it central bank. And the reason why it recognizes things is because I guess I typed things earlier and I tested that things work. So the AI already picks that up. It's crazy. So, okay. So it takes an agent. Okay. So let's use this to describe what the class is doing. Okay. So let's define the init. So let's define what happens when we initialize an instance of this class. So, okay, let me walk you through. Since things are recognized, I don't need to spend too much time, I guess. So these are the member variables for the class. So it comes with a reserves variable, which is equal to 10,000 by default. We can change that when we initialize an instance of this class called central bank. The money creation threshold is 0.2. And we set that here. And model is passed at initialization, and the model is something we will create later. So basically, every agent in Mesa inherits from the agent class, this agent class, okay? And our central bank will start with 10,000 monetary units in reserves and has a threshold for when it should create money. When local banks have less than 20% of the central bank's reserves. Okay, so that's the story. And let's define, okay, if you see, one of the central crucial elements of agent-based modeling is that you have to define a step, which is what happens after one step is taken, okay? And the step takes in, it acts on the class itself. I hope this makes sense. So the step in this case will act on the central bank itself. So define step and self, okay, and then we have to say check, okay, check if bank reserves. Okay, so in each step we have to check if bank reserves are too low, and if they are, create new money. Okay, so local banks are not defined yet, but this is the next agent we will define. Okay, so local banks, this is a local variable now, is equal to self dot model, and model is something that will be created. The model is what's gonna orchestrate what the central bank agent, the local bank agents, and the person agents will be doing. Okay, so what we do here is to store all local banks into this variable called local banks, this one. Okay, and the local banks will be taken out from the model itself. Okay, and we do that by using this function agents by type, and the type is local bank. Okay, we haven't defined the local bank agent yet, but we are already using it. So in the next step we will do something like class local bank and then agent, and then we will define the local bank. Okay, I hope this makes sense, but this variable stores all the local banks. And let me show you agents by type. It's a dictionary that shows a dictionary where the keys are agent types and the values are the corresponding agent sets. Okay, let's go to the documentation to get a better understanding of what this does. So agents by type, so you see that this is come on, I forgot the name. It's a member function of the class model. Okay, agents by type. So if we go down, they don't say anything about that. Okay, let's see what an agent set is. Agent set is a class. It's a collection class that represents an ordered set of agents within an agent-based model. This class extends both mutable set and sequence, providing set-like functionality with order preservation and sequence operations. I'm sorry. So, okay, it pretty much collects all local banks, okay, into a dictionary. Right, so if local banks exist, so in other words, if that local variable is not empty, we have to calculate the average reserves, and this is equal to the mean, and this is an numpy function of all bank reserves, so b dot reserves. So each local bank will have a member variable called reserves, which is going to store how much money they have. Okay, for b in local banks. Okay, so this variable will store a number, okay, which is the average reserves. If the average reserves are less okay, let me think. Okay, this is a central bank, so self dot money creation threshold times self dot reserves. In other words, if these reserves of the local banks are less than the money creation threshold, which is 0.2 times the reserves it has. In other words, since the money reserves are 10,000, then if money drops below 2,000, okay, if the money in the local bank drops below 2,000, we have to create money, okay? Let's create an amount equal to 5,000 and then self dot reserves gets enhanced by that amount. So we create money out of thin air, okay? That's the part, the cool part, okay? Then for bank, in local banks, okay, we add to their reserves as well, okay? So we distribute that amount to the banks equally, okay? So if you have 10 banks, they will get 500 bucks, 500 units, I'm sorry, of money each, okay? So to summarize, what this class does, it creates a central bank agent, okay? And it inherits from the agent class of Mesa, okay? The central bank comes with some reserves, which we preset equal to 10,000, but we can change that if we want. And the money creation threshold is 0.2, right? And in each step, we first get all the local banks, which is the next class we will create. And we check how much money they have, and if the money is less than 20% of the amount that the central bank has, we will create money. That's it, okay? So so the interesting part, I guess, is that the central bank just creates its own reserves and increases the reserves as of all local banks equally. So this is kind of similar to how the real world works. I mean, the role of a central bank is to inject money into the economy, pretty much, okay? Right, okay, so let's keep it there. All right, so the next in line is to create the local bank agent. And we can do that by defining local bank, and the AI already knows what I did before, so it gives me back what I typed in earlier. So this is the local bank that lends money to people. Okay, I can go with that. To initialize it, okay, it takes an agent again, because this is an agent, okay, just like the central bank. And this time it doesn't, this bank does not create money because it only gets money from the central bank, okay? But it lends money out to people, okay? So therefore, when we initialize it, it takes in the model we will define later, and a function and a variable called reserves, which is preset to 1000, and it initializes this member variable to be equal to 1000, pretty much, okay? So each local bank starts with 1000 monetary units in reserves, and these reserves come from the central bank and are used to make loans to people, okay? So now, just like before, the most central element in agent-based modeling is the step function. So what happens after each step? And this time, and in this model, we are talking about the time step. So in each step, okay, we find people that need loans as good predators that we are. Sorry, I'm kidding. We find the people. Okay, let's go with that. We find people who need loans and lend to them if we have reserves. So for person in self.model, the model is going to be defined later. And again, we use this function agents by type. Okay. And the type is person. Okay. We select from those people the persons. Actually, let's do this as a lambda function. P dot needs loan, and needs loan is a member variable of the person class, which we will define later. Okay. Then if self dot reserves is larger than 100, okay, which means that there are some reserves left in the local bank, we loan an amount of 100 to the people, so our reserves will be reduced by that amount, right? So self dot reserves will be reduced by the loan amount, but the person's wealth will increase by that same loan amount, and the person will no longer need a loan. Okay, so this will be set to false. And as we will see when we will define the person class, whether a person needs loan will be a Boolean variable, which will be determined randomly. Okay, we will use a random number and a probability. So we will set the probability to say 0.5 and then generate a random number between 0 and 1. If the random number is less than 0.5, then the person will need a loan. And if it's larger than 0.5, it will not need a loan. So simple like that, okay? Everything is random in this model. So to summarize again, at each step, local banks look for people who need loans. If a bank has enough money, which we define as 100, more than 100 actually, it lends 100 units to the person. And we filter the people who need loans by using this select function, which is a Mesa function. Okay, so select is a function that selects a subset of agents from the agent set based on a filter function and or limit. Okay, and yeah, this is all they give you here. Okay, that's cool. Let's initialize this and move on. And last but not least, in terms of agents, is the person class. Okay, is the person agent. So you know the drill by now: class, person, agent. And okay, the AI will tell me, okay, great, this is what I typed in earlier. So okay, the person can invest money, consume money, or need loans. Okay, so this means that this pretty much means three member variables. Okay, the one is going to tell you whether the person will invest or not, the other will tell you whether it will consume or not, and the third and final member variable will tell you whether the person needs a loan or not. Okay, so the initialization is the same. And okay, okay, something went wrong. Let me check. So to initialize this model, we need a probability to invest, which is 0.3. and we use the super dot init and then model, which is standard for all agents in Mesa. We found this. Let's go back. Oops, let's close this actually. There you go. Okay, so you see how when you initialize agents, you have to pass in the model. And as we will see in a while, in a moment, when we initialize a model, we just do the init. We don't pass in anything. Okay, so, but something bothers me here. Okay, so a person is defined and has 100 units of money. It has an investment probability, and it needs a loan if random.random, which gives you a random number, is less than, let's say, 0.5. Okay, so yes, random.random generates a random number between 0 and 1. So if I initialize it a couple of times, you see how it gives me a different number between 0 and 1 each time. Okay, so let's delete this. We don't need it. Actually, this one. Okay, so 3 member variables for our person. Okay, wealth, probability to invest, or probability to take a loan. Actually, this is a yes or no. It's a Boolean variable. Okay, the way we define it is, let me show you, 0.7 less than 0.5, the output is false, right? But if we do 0.2, the output is true. Okay, so this is what this member variable does. Okay. Again, this is an agent-based model, so we need to define a step. Okay, which takes in itself, and here we will decide whether to invest or consume. So if self dot random is, so the probability to invest is kind of random pretty much, okay, is less than self dot investment probability. So let me see. So what we did here is to generate a random number, and if that random number is less than 0.3, we will invest our money, okay? And if we invest our money, our wealth will increase by a random number, which will be drawn from the uniform distribution between 0 and 10. So we might invest and get no money. We might invest and our wealth will be increased by 10, or anything in between. So that's the idea. And let me show you this function here. So you see it gives you a number between 0 and 10 pretty much, okay, and it's random. So you see you got 1, 3.6, 4.62, 8.93, etc. And okay, otherwise, if the random number is more than 0.3, okay, so most probably we will not invest our money because we are degenerate gamblers and consumers, right? So so most probably we will just waste our money, and when we waste our money, we consume between 0 and 5 of our wealth, okay? And in this model, people will not go into debt, so we will set the wealth. Okay, so we will use this function that says max self-wealth and 0, which means that if our wealth goes below 0, our wealth will be set to 0. That's it, okay? Because you don't want people to go in debt in this economy, okay? So let me show you how this works. So this function just returns 10 now, but if we do -9, it will return 0, okay? because it's the maximum between these two numbers. I think it works with more numbers as well. You see, so you can enter as many numbers as you want. Okay. Brilliant. We defined all of our agents. So to summarize the person agent, each person starts with 100 units of wealth, has 30% probability of investing at each step, and when created, it has a 50% chance of needing a loan. Okay? So, and all of this is random, okay? And at each step, a person decides whether to invest or consume. If they invest, they gain between 0 and 10 units of wealth. If they consume, they lose between between 0 and 5 units of wealth. And their wealth cannot go below 0. Okay. I wish this was true in real life as well. As we all know, actually people can go into debt, in which case they have a negative wealth, which is crazy to me, at least. I hope I never get into debt, but yeah, it's not a pleasant feeling. All right, so we have 3 agents. Now let's go see how to define the model. So class economic model. Okay, and this does not take in an agent, it takes a model. Okay, and they have an example here, okay, which has a self.grid. So it has a grid member variable, which is a grid environment, I guess. That does what? Let me see. So the agents in this simple model they show here are just people, I guess, with some age, and in each step their age increases by 1. And then the model defines a grid, and the initial age of the person is between 0 and 80. Then they create an instance of an agent with some initial age, some random coordinates, and they place the agent at some random coordinates. And in each step, self.agents shuffle do step, and the step just increases the age by 1. Okay, that's a simple model. In our case, what we will do is, okay, I think this is called the Shebang, Shebang Python. So, okay, yeah. So it's a model. So the economic model is a model of a 3-tier economic system. Okay, so the model is defined with 50 people by default, 3 local banks. The central bank is there by default. The money creation threshold is 0.2, and the seed is none. Okay, we can define a random seed so that results are reproducible pretty much. Okay, and we define that init function. Okay, so let's create agents. Create agents. Okay, so we need a central bank, self money creation threshold, and okay, let me see if this is correct. Okay, central bank. Okay, the reserves are fixed, and the money creation threshold is also fixed. Okay, this is good. And then local bank so we create as many local banks pretty much as this variable here, 3. Okay, and this will be a set in square brackets. Same for persons. So the model takes parameters for the number of people, the number of banks, the money creation threshold, and an optional random seed. We first create the central bank, then the specified number of local banks, and finally all the people. In Mesa 3, we don't need to manually assign unique IDs or add agents to a scheduler. Mesa handles all that automatically now, which is nice. Okay, so this is written in my script here, okay, in case you're wondering. And okay, we will now use a data collector, and the data collector tracks several metrics throughout the simulation. So we will track the Gini coefficient. We will define that later. The Gini coefficient measures wealth inequality. Let me show you. So Gini coefficient. So the Gini coefficient is a measure of statistical dispersion intended to represent the income inequality, the wealth inequality, or the consumption inequality. Okay, it has a history, and this is the definition. The Gini coefficient is equal to the area marked A divided by the total area of A and B. Okay, and this is the line of equality. And this is the cumulative share of people from lowest to highest incomes and the cumulative share of income earned, okay? So you can pretty much see that the Gini coefficient will be larger if, let me think. So if you have too few people with high incomes, pretty much, okay? Okay, so we need this data collector. So this is the data collection where we collect both model level and agent level data. Okay, so self dot data collector is defined as data collector, which is a function we imported, remember? So if we go up here, we actually imported this from Mesa. Okay, so we need to define model reporters, which is equal to okay, is this the proper way? Okay, yeah, okay, that's good. I'm worrying about the indentation in case you're wondering. Okay, right, so we need the Gini coefficient, which is defined as a lambda function m equal to compute Gini coefficient m. Okay, the mean wealth, total money. I'm gonna explain. Let me type. Okay, so agent. So here is an instantiation of a money model that they have here as an example, and I stole many of the ideas from here pretty much. Okay, so here they do Mesa.data collector because they don't import the data collector class, but we do in our case. So you have to define model reporters and agent reporters. In this case, they define the model reporters to report the Gini coefficient and the agent reporters to report the wealth, okay? And here's where they define their agents and their step function. And you will see that we will actually use that as is, okay? We will pretty much copy it, okay? So in our case, the data collector is a little bit more involved. Actually, let me write it like this. It might be easier to see. Okay, so right, so the model reporters in our case are we need to report the Gini coefficient that will come from the people. As we will see, the wealth of the people. The mean wealth is also going to come from the agents type person. Okay, so we will calculate the mean wealth of all the people. The total money will be the total money of all the people. Okay, so it's yeah, that's self-explanatory, I guess. We will also report the central bank reserves, which we will just do by aggregating the reserves of the central bank, and then the local bank reserves will also be reported by collecting through this lambda function the agents of type local bank, and we will collect from the local banks the reserves and sum them. Okay, and from agent reporters we will report the wealth of each person. Now comes a crucial step. And the crucial step is the step function, okay? So let's do define step. The AI already did that for us because I typed it in earlier. Let me just check. So to advance the model by one step, we will collect all the data from the data collector, okay? So we will be using that, and collect is a built-in command that collects all the data as defined in here. And we will advance the agents by one step, okay? So the model will pretty much call the step function of each agent in each step, okay? So we have one step function per agent, and this is what the model does, okay? And let me see. Okay, what else do we need? We need the Gini coefficient. We haven't defined that, so define, let's see. Yes, the AI figured it out. So compute Gini coefficient. Right, so the Gini coefficient is defined, and we are left with just running the model, guys. That's it. So define, run simulation. And the number of people is 5,000 now. Number of banks is 50, and we take 1,000 steps. These are time steps. And we just have to create and run the model. So create and run model. And the model is simply our economic model, which we defined above. For n people equal to 5,000, banks equal to 50, steps 1,000, and no seed. And then for we run this loop, the model is takes a step for each number. It starts from 0, 1, 2, 3, all the way to 1,000 iterations, pretty much. Okay, so I ran into trouble with some of the code earlier. So here is the clean version of the code. Basically, here is the economic model we defined. Nothing's different from what you saw earlier. Here is where we compute the Gini coefficient, and here is where we run the simulation. And the most basic part is actually this one, okay? It's where we define the economic model and do a step for each number of steps we define, okay? And here we have some getter functions. So the model data and agent data refer to, we go to the model data collector, which is the member function, this one. And remember that we have all these dictionary entries which represent data in data frames, right? Okay, so here we get the get model vars data frame, and the get agent vars data frame. These are built-in functions built into Mesa. Okay, it creates a pandas data frame from the agent variables, and the get model vars creates a data frame for the model variables. Okay, so in the model variables in our case are these variables, and the agent variables is just the wealth. Okay, and the final wealth is comes from the agent data, and it's from the last step pretty much. Okay, so we get the last let me actually show you. Let's do print model data. It's gonna be a huge data frame with 1000 entries, guys. Okay, so that's why I didn't do that. So but let me show you anyway. So okay, here we make various plots. We use the PLT, the matplotlib library, and we print the wealth distribution histogram, the Gini coefficient evolution with each time step, the total money in the system, and the bank reserves over time. Okay. This I'm gonna comment out for now. And yes, we returned the model pretty much. Okay, so if we run this simulation for, and I made a test run here. So for 1000 steps, you see how most people end up with no money, okay, just like in real life. And very few people end up with lots of money. So these people got lucky through their investments and so on. This is a very simple model though, okay, very, very simple model. But this is the number of people. So we have, we run the simulation for 5,000 people, and 1,200 of them already have money between, don't know, 0 to 10, something like that. And the wealth inequality over time increases, which is, I think it's observed in real economies as well. The total wealth in the economy decreases, but the bank reserves increase over time. And the Lorenz curve, did I comment it out? I didn't comment it out. But anyway, let me run one more simulation. Let's do 1,000 people and 5 banks and 1,000 steps. See you in a while. Okay, we see a similar phenomenon, okay, with most of the people ending up with no money again. Okay, let's do 5,000 steps, see if something changes. Okay, for 5,000 steps, as we see, some people get lucky actually, and they have a lot of wealth. But the Gini coefficient increases and stabilizes at about 0.55. Okay, bank reserves and central bank reserves increase. Total money in the economy kind of flat out at some point. Let's do 10,000 people, 50 banks, 1,000 steps. Okay, let's see what happens. Okay, let's study the results of having 10,000 people, 50 banks, and 1,000 steps. Again, the Gini coefficient increases and then stabilizes with time, okay, at about 0.55. So this is a very unequal economy, okay. And we see again the same phenomenon that the wealth of the people decreases. Okay, let's see what happens if we change some parameters. So let's run one more experiment with more banks, okay? Let's say we have 1,000 people and 500 banks, so people can get loans like crazy. So let's see what happens. Okay, with 500 banks, so too many local banks, actually the number of people that end up poor increases, which is crazy, okay? All right, so let's do some modifications. So let's go back to the person agent class and increase the probability that they invest. Okay, let's see. So let's see what happens now. Now 1,000 people and 50 banks is still there, and let's run the simulation. Wow. Okay, that's crazy. So we end up with a very equal society. Like the Gini coefficient is almost close to zero. So 0.075. That would be a dream economy, I guess. Okay, by the way, I talk about the economy just as if I am an economist. I'm not. I'm just playing around with code, okay? But we get like a Gaussian centered around this wealth, okay? Okay, we still get some number of poor people, but actually the majority of people end up being rich, okay? And the wealth in the economy increases. Wow, okay, that's great. And this is just by increasing the probability that people invest, which is crazy. Okay, let's decrease it to 0.4 and let's run the simulation again. Okay, still we get lots of rich people and a very low Gini coefficient. Okay, I don't even know if these results make sense, guys, by the way. Okay, in a real economy, okay, let's see. Let's ask the question, how many people, what percentage of people, okay, what percentage of people invest their money? UK, approximately 23% of adults. Okay, let's do the 23%. So, economic model, person, let's do 0.23. Okay, that's the investing probability. And let's see what happens now. Okay, with 0.23, the Gini coefficient actually increased. Now it's over 0.6. Okay, and most people end up poor. Okay, that's sad, I guess. The total money in the economy, you start out with lots of money. By the way, 100,000 means we have 1,000 people, and each person has 100 money units, remember? So 100 times 1,000, 100,000. So that's the money, that's the total wealth in the economy, okay? And this decreases because this money end up back to the bank, okay? And the money increase for the bank. So the bankers get all the money in this economy. That's crazy. Okay, let's do, what else can we try? We increase the number of banks, that does nothing, as we saw. Let's, okay, one more experiment. And this is the essence of agent-based modeling. You can just run experiments forever once you define your agents and so on. Okay. Let's allow the central bank to have more money. Let's see what happens now. Okay, let's refresh all the functions just in case, and let's run the simulation and see what happens. By the way, I forgot that we actually print the data frames, and you see, okay, so in each step, we get the Gini coefficient, the mean wealth, the total money, the central bank reserves that eventually increase, the bank reserves, and the agent ID. Okay, I don't know what that is. I guess it's we'll have 1,000. Yeah, okay. These are our agents, like the persons, plus the banks. So we should have 1,051 agents, right? And this is what we see here. We have 1,000 people, 50 banks, and one central bank. So that makes sense. Again, increasing the wealth of the central bank actually destroys the economy. So anyway, this is the video, guys. This is, I don't claim to have any deep knowledge in agent-based modeling. I just found it fascinating when I was introduced to it. I was unaware of its existence until 2023, so about 2.5 years ago. And when I started out, I was playing around with NetLogo, and I worked on a project for about 1 year without making a lot of progress. I would like to make more progress, but I didn't. But later I found out about Mesa, and I always wanted to make a project with it. And I'm happy that this kind of worked. Let me know what you think. I'm gonna create a GitHub for this, and I will have the link in the comments so you guys can experiment with it and make pull requests and improve the code. And I invite people who are economists or agent-based modeling specialists to let me know whether this makes sense or not, like if this is something useful, or I don't know. This is for educational purposes and my personal education, because I didn't know much about this before this project. So it's kind of cool, I think. Let me know what you think. See you in the next video.